What you see here are 24 circles, 6 rows of 4 circles each, tightly packed in this rectangular frame. So the question is, can I squeeze in this additional red circle somewhere in this frame? It seems impossible as there appears to be no additional room for this circle. But as I showed you in the video link below, playing with carom coins, I achieved exactly this. And I could achieve this by reorganizing the circles or the carom coins from the square pattern shown on the left to hexagonal pattern on the right. So the hexagonal pattern is obviously a much more efficient way of packing circles. Let's look at it quantitatively. We begin with a square packing of circles. We define packing efficiency as the ratio of area occupied by circles to the total area. For a periodic pattern like this, it is much more easier and efficient to do the calculation for a unit cell because the whole periodic pattern can be constructed by repeating identical unit cells. Packing efficiency within a given unit cell can be considered as packing efficiency of the entire pattern. In the case of the square packing here, the unit cell, the efficient unit cell or a convenient unit cell is a square itself with its corners at the centers of neighboring squares. Now, if we look at this unit cell, we can see that there are pieces of 4 circles in this, and each of these pieces is actually a quarter circle. So effectively, there is 1 circle in this unit cell. Packing fraction becomes area of the circle divided by area of the square. We can quickly do this calculation. Pi d square by 4 divided by d square, where d is the diameter of the circle. D square cancels, giving us the value of pi by 4. Numerically, this is about 0.745. So, about 74% of the area is occupied by circles. For the hexagonal packing, the unit cell is the rhombus shown here. And if you look carefully, there are 4 pieces of circles again within this rhombus, and they again add up to 1 circle. So the packing efficiency is again area of a circle divided by area of the rhombus, and if we do this calculation, we find that now packing efficiency is 0.906. So about 90% of the area is occupied by circles, a significant improvement over 74% of the square pattern shown before. So this improved packing efficiency is what allows me to accommodate this additional circle in this case. Careful viewers must have noticed that there is additional space at the top and bottom of the frame in the case of square packing. This is necessary because 7 rows of hexagonal packing actually require a slightly more height than 6 rows of square packing. We can do this calculation by introducing this right triangle ABC. The hypotenuse of this triangle AB is equal to 6 times the diameter. So the height AC is AB sine 60 degree, which is 5.2 times the diameter. The total height of the frame requires us to add a radius at point A and a radius at point C. So we add a diameter to AC to get 6.2D as the height of the frame. This figure summarizes our calculation, showing the additional height of the hexagonal packing in comparison to the square packing. I end this video by pointing out that the packing of circles which we have considered are analogous to packing of atoms in cubic close packed structure. So the square packing actually corresponds to the packing of atoms in the 100 plane of cubic close packed structure, whereas the hexagonal packing represents the packing in 111 plane of cubic close packed structure. I leave you to think about that. Thank you very much for your attention.